Hello, and welcome to your Week 9 lecture video. This week we're going to look at ICMP, the transport layer, and then we're going to do a little bit of subnetting at the end, and that's how it's going to go. Take notes of anything that you have questions of, and ask me in the lab. So ICMP is something you've been using. You just don't know you've been using it. I'm going to explain that a little bit more momentarily. ICMP stands for Internet Control Message Protocol. And it provides feedback about issues related to processing IP packets under certain conditions. ICMP version 4 is a protocol, or the version of this protocol for IPv4. Of course, there's an ICMP version 6 for IPv6, and the IPv6 one includes some additional functionality. ICMP messages for both version 4 and version 6 do have some common ones: host reachability, destination or service unreachable, and time exceeded. I was going to leave it for the next slide, but you've been using this. You just didn't know you were using it. ICMP is the protocol that the ping command uses. And you've used ping extensively this semester. So anytime you're using ping, it's running on ICMP. Although there's some other stuff that uses ICMP as well. So we use this commonly for testing connectivity over the network, right? As a first test to see if you've got a connection. The first packet that goes out is an ICMP echo request. And that goes usually from one host to another host. It could be from a router's command prompt. And it just simply says, hey, are you there? Right? It goes directly to an IP address. If the host is available, it responds with an echo reply, which means, hey, yeah, I'm here. What's up? Now, there's a variety of reasons, if you don't get a reply, why that could be. It could be unreachable. And that message can be used to notify the source as to why that service is unreachable. There's a couple different codes for ICMP version 4. These are included in the packet as to why it couldn't be delivered. If it's a 0, the network is unreachable. If it's a 1, the host is unreachable. A 2, the protocol is unreachable. And a 3, the port is unreachable. ICMP version 6 has slightly different codes, and they are as follows. If it's a 0, there's no route to the destination, which is a little more descriptive than network unreachable, right? 1, communication with the destination is administratively prohibited, usually meaning a firewall. 2, beyond the scope of the source address. 3, the address is unreachable. Or 4, the port is unreachable. So there's a bit more functionality that's been added. And this is to, of course, make troubleshooting a little easier. Now with ICMP packets, there's a time to live field. Well, with most packets, there's a time to live field, right? We've seen that commonly. But with ICMP, when that time to live field is decremented to 0, ICMP version 4 sends a time exceeded message to the host. ICMP version 6 will also send that, but instead of using the time to live field, it uses the hop limit field in the IPv6 packet. So here we go. We see expired in transit. That's similar wording, right? Means it didn't get there, right? The packet didn't make it. It timed out. Now, these sort of messages are commonly used by another tool or command we've used, traceroute. And I've shown you that you can use that in Windows, in Linux, and Cisco, right? Any operating system you can use ping and traceroute. They're useful things. Now, ICMP version 6 added a whole bunch of additional functionality that's not in ICMP version 4 at all. These are both part of the Neighbor Discovery Protocol, or ND or NDP. Messaging between routers and devices for using IPv6. For dynamic address allocation, router solicitation messages and router advertisement messages. We looked at these in the previous lecture, right? Those use ICMP version 6. Also, if you're running DAD, duplicate address detection, which we talked about in a previous lecture, it's for if you randomly generate your IP address, determining if it is unique, uses ICMP version 6 for neighbor solicitation and neighbor advertisement messages. So lots of things that we use ICMP for that we didn't used to. Router advertisement messages are sent by IP version 6 enabled routers every 200 seconds, and they provide information about the network to IPv6 enabled hosts. These can include things like addressing information, like your prefix and the prefix length, DNS information, your domain name, and if the host is using SLAC, stateless address auto configuration, it will set its default gateway to the link local address of the router that sent that router advertisement, so it knows how to get outside the network and who to talk to get more information. An IPv6 enabled router also sends out a router advertisement message in response to a router solicitation message. And here we have an example of that happening. The PC came online, needs to figure out how to get its IPv6 address, so it sends out a message and gets a reply. We've looked at this previously, right? Right. Now, devices that are assigned global IPv6 unicast or link local addresses might also perform DAD, duplicate address detection, and that again uses ICMP, because in IPv6 there's no broadcasts, right? For determining the MAC address for a destination, the device will send a neighbor solicitation message to the solicit node address, and the message will include the known IPv6 address. If it gets a response, then it knows that it's not a unique address, right? The other place we see ICMP, of course, is ping and traceroute, which I talked about earlier. So we use these from the command line to test connectivity, right? Usually you ping the domain name or fully qualified domain name or IP address that you're trying to communicate with to see if you've got a successful connection or not, right? You can use this to verify that your configuration is correct. You can use this to help troubleshoot things if things aren't working and see where things are not working. Usually if your network connectivity is an issue, you try to ping your default gateway and see what happens. Here's an example of the ping command with both IPv4 and IPv6. If you receive a response, then you know you're good, right? Sometimes that first one will time out because it takes time for ARP. It's pretty common. The amount of time it takes for ARP makes ping timeout. But usually only one or two packets. If it's timing out a lot, you got something else going on. You can also use ping to test and see if your IP stack is working correctly by pinging your local host, your loopback address, right? 127.0.0.1. For IPv4, for IPv6, it's just :1. And that will tell you if TCP/IP is working properly or not. If it's not, yeah, try rebooting. Maybe that'll fix it. So pinging your default gateway, I already talked about, right? But here it is. Common thing to do because it tells you, it helps narrow down where the problem is, right? If you can't ping your default gateway, you should check your cabling. You should make sure it's up and functional, make sure it's been configured. Make sure you've got the correct default gateway set. Could be any of those 4 things. It could be other things too. You could also use it to connect or test connections to other devices on the local network and out on the internet. It's a very common tool. However, a lot of network admins prohibit ping internally for security. So it's a useful thing, but you might not have access to it, which you don't at Centennial, right? Now, why do they prohibit ping? Because it can be used to perform a distributed denial of service attack, which we're going to talk about more in a later lecture. Now, if you're trying to connect to something that's more than 1 hop away with ping and it's not working, maybe it's on the local network, maybe it's out on the internet, you might want to use traceroute. Traceroute gives you a bit more information. Ping just tells you if that IP address is reachable or not, or that fully qualified domain name. Traceroute will show you exactly where your packets are getting to before they start dying. And here's example output here. It'll also tell you how long it takes. So if your network's really slow, you'll figure out where that bottleneck is. Or if things aren't getting past a certain point, you can figure out where that is. If you've set up static routing, which you're going to learn about next semester, this will help you figure out, okay, well, it's getting to this router and then it's stopping. Maybe I should go look at that router and check its routing table, see if it's been configured properly. And also check and make sure that its interfaces are in an up status, right? Because if they're not, it's not going to work. There's a little bit more about how traceroute works, but kind of unnecessary. Ping and traceroute we use to troubleshoot network issues. Super common tools. At this point, I would ask you if you have any questions. However, since this is a lecture video, well, I'll still ask if you have any questions. Please bring them to class, and we'll talk about them there. All right. So chapter 13 out of the way, on to chapter 14, transport layer. So we're going to look at all of these things today. We're going to look at TCP, we're going to look at UDP, we're going to look at ports and how communication works and flow control and all kinds of useful stuff. So the transport layer, and there it is in our TCP/IP model. In the OSI model, that's layer 4, right? TCP/IP model, it's layer 3 right here. It's responsible for logical communications between your hosts, your applications running on different hosts. This links your application layer with the lower layers, and it's responsible for making sure packets receive or are received by the right application on both ends of the spectrum, or both ends of the communication, rather. I don't know why I said spectrum. So the transport layer has several responsibilities. It tracks individual conversations, it segments data and reassembles those segments, it adds header information, and it will identify, separate, and manage multiple conversations on a single device, on multiple devices. It's useful. It uses segmentation and multiplexing to enable different communication conversations so they can be placed on the same network without having packets ending up to the wrong device on the other end, or to the wrong application even, right? So here's an example here. You've got a PC. It could be browsing multiple web pages at the same time while streaming a video, maybe chatting online, maybe doing some, I don't know, instant messaging. That's pretty old, but I guess kind of like that, yeah. And maybe email, right? All of these different applications are going out over the same network media. How do all the packets make it to the right applications? Transport layer does that. Transport layer does all of that. Now if we look at IP for a second, the IP protocol, or IP protocol, doesn't specify how the delivery or transportation of packets has to take place. All it specifies is where they go. The transport layer is responsible for figuring out how to make that happen. It specifies how to transfer messages between hosts and is responsible for managing reliability requirements if they're available. And there's two protocols we look at the transport layer, TCP and UDP. TCP, or Transmission Control Protocol, gives you reliability and flow control. It allows you to, well, it allows the network and the host and the software that's running to do all of these things, right? To number and track the segments that are transmitted from a specific host to a specific application, acknowledge the received data, and because there's acknowledgement sent, it can retransmit anything that wasn't acknowledged. And also, because there's sequence numbers in here, data can be put back in the proper order because it might arrive out of order. And it sends data at an efficient rate that's acceptable by the receiver. So as soon as, we're going to look at this in a minute, but as soon as packets start getting dropped, it'll back that off, right? UDP, on the other hand, it's pretty much the opposite of that. It's a very basic protocol. It delivers datagrams. UDP is User Datagram Protocol. Between appropriate applications, there's very little overhead and error checking. Almost no error checking. In fact, there is no error checking. It's a connectionless protocol. It's known as a best effort delivery protocol because there's no acknowledgement that the data is received at the destination. I'll tie these up with some jokes at the end, but TCP makes sure that your packets get there, but it's got all this overhead. It's a bit slower. UDP is good for faster things. It just doesn't care, right? It doesn't have any mechanism to care if the packets are get there. It can't check, but it's good if you need speed. So UDP is used by applications that require a large amount of overhead and very, very quick, I was going to say low latency. If it's important that all the data arrives and can be processed in the proper sequence, it gets put back together, you use TCP. Otherwise, you use UDP. So UDP is fast. It doesn't have a lot of overhead. However, because it's fast and there's not a lot of overhead, there's no acknowledgement. Any resent or lost data is not resent. And if data arrives out of sequence on the other end, it doesn't care. It just goes to the next thing. We use UDP for things like VoIP, DNS, streaming video, gaming. I'm sure we've got a few gamers in the class. If you ever played an online game and seen your character jump across the screen, or like obviously uncontrolled, right? Not actually jumping in the game, or you know, everything really slows down for a second, then speeds up really, really fast, and then catches up. That's UDP. The packets arrived out of sequence, so UDP just went to the next one. And they didn't arrive for a bit, so that's why it was stuck there. TCP is the opposite of all those, right? It's reliable, it acknowledges data that's been sent, it resends lost data, and it delivers data, or it puts the data back into the sequenced order, right? It's delivered with sequencing, so it can be put in the proper order. So we use it for things like email, browsing the internet, things where you want to make sure that all of your data is there, right? Because if some of the words were missing out of your email or your web page, it'd make it hard to read. So that's our overview, right? We're going to look at each of those in a bit more depth now. TCP, it's connection oriented, right? That's the one we're going to use when we want to make sure that the data gets there, and if it doesn't get there, it's resent. So it establishes a session. It's a connection-oriented protocol. It negotiates and establishes a permanent connection, which is referred to as a session, between a source and destination device before any traffic's forwarded. And it maintains the session throughout the duration of the communication. For a variety of reasons, segments might become corrupt or lost as they're transmitted over the network. TCP makes sure that each segment that's sent arrives at the destination, and if it's not, it will retransmit it. Also, since packets might take, or segments, might take multiple routes, right? Data might arrive out of sequence. TCP will put them back in the right order. And it supports flow control. Flow control is a good thing because networks have limited resources. They have limited amounts of memory and processing power and bandwidth. TCP can sense that these resources are overtaxed, and it can request that the sending application just slow down a bit. You're talking too fast, right? Just slow it down. I'm losing some stuff here. Yeah, there we go. Right, that's what TCP does. Here's what a TCP packet looks like. Of course, this is a diagram of what it looks like, right? It's all binary. So on that packet diagram we've seen, we see a source port and a destination port. These are 16-bit fields to identify the source and destination application by port number. There's common port numbers, which we're going to look at. A sequence number, so this is a 32-bit field, and it's used to reassemble the data in the proper order. And an acknowledgement number, this is used to indicate that the data has been received and what the next byte is expected to be from the host. A header length, it's a 4-bit field. It's known as your data offset, and that indicates the length of the TCP segment header. There's a 6-bit reserve field for future use, just because we might need something later. There's also a 6-bit field for control bits. So these are codes or flags which indicate the purpose or function of the segment. There's a window size, that's a 16-bit field, and that's used to indicate the number of bytes that can be accepted at one time. There's a checksum field, so that's used for error checking for the segment header and the data, 16 bits as well. And an urgent field, so that indicates whether the data is urgent or not for quality of service, right? That's 16 bits as well. So TCP does all kinds of things, right? It divides up your data into different segments. It gives you reliability, flow control, make sure everything's properly reordered, and make sure everything ends up at the right place. And if packets arrive at a sequence or don't arrive at all, they get resent. If they are at a sequence, they just get put back in the right sequence. UDP, I've said this a few times, right? The opposite of that. So with UDP, data is reconstructed in the order that it's received. Any segments that have been lost or arrive late aren't resent at all. If they just arrive late, they're dropped. There's no session established prior to data being sent. They just start sending data, and they don't care if you're ready. And the sending party isn't informed about any resource availability because UDP has no mechanism for learning about that. Because it's a lot simpler, the header's a lot simpler. There's only 4 fields required, and it's 8 bytes in total. It's a 64-bit field. Much smaller overhead, right? So we've got a source and destination port. These are both 16-bit fields. Just like with TCP, they identify the applications by port number. We've got a length field, so that indicates the length of the datagram header. A checksum that's used for error checking on the header and data. We can still check the data to see if it's corrupt, and if it's corrupt, just drop it. That's pretty much all that happens there. So applications that use UDP, anything that needs high bandwidth, right? Streaming, VoIP. VoIP requires high bandwidth. It needs very minimal delay. Streaming video, DNS and DHCP, believe it or not, also use UDP. Why? Because if it fails, we can just send a new one. It's okay. We want it fast. SNMP for remote management, TFTP, yeah, all use UDP. Now we've talked about port numbers a little bit, right? What the hell are port numbers? You're probably wondering. Well, TCP and UDP both use port numbers to manage multiple simultaneous conversations. There's a variety of different port numbers that are associated with different protocols, as we're going to look at, and these are bound to originating applications. For the source port and for the destination port, that's where it's going on the remote host, right? Remote host. It's where the data is being sent to. Combined, these are a socket pair. The segments are then encapsulated within an IP packet, and not combined. The source IP and source port number, or destination IP and destination port number, that's a socket, right? So we got two pairs of sockets here: source and destination IP, port and IP, or source IP and port, destination IP and port. Sockets allow you to have multiple processes running on a client, and they distinguish each other from other conversations on servers, right? It's just a useful thing. This is how, if you've got like 20 browser tabs open at the same time, this is how it all works, right? Now, we've got 65,535 ports available to us. Why? Because that's a binary value, right? And they're broken down into three groupings. Your well-known ports between 0 and 1023. So these are port numbers that have been reserved for common services that we use all the time that have been around for a long time, like web browsers, email, remote access. There's a bunch of defined well-known ports for common applications, and you're going to see these port numbers come up time and time again for a variety of different things in networking, usually things like firewalls, right? Allowing traffic on a network, you need to know the port to allow. Registered ports are between 1024 and 49,151. These are assigned by the IANA to anybody requesting one with a specific process or application. And these are primarily used for individual applications that somebody's installed. Like if you've got proprietary software, you're going to have to, if it's got network functionality built into it, and you're doing something funky with it, you're going to have to apply for one of these, right? An example, Cisco registered port 1812 for its Radius server authentication process. That's what Radius servers do. They're Cisco products that authenticate devices. Now, anything from 49,152 up to 65,535. These are dynamic ports. They're chosen by the client's OS when a service is initiated. So well, you're going to see in a minute, right? The source port coming from the client will be one of these ports, and the destination port going to the destination will be whatever the common port is for that thing. Hopefully that makes sense. Common ports that you tend to see, FTP uses 2, 20 and 21. 20 for the data, 21 for your controlling your session. 22 is for SSH, which is what we should be using. Telnet, that's 23, which we shouldn't really be using, unless you want to watch Star Wars from the command line. Have I showed you that? I'll try to make a note to remember to show you that at the end of today's lecture. Now, Telnet, of course, can also be used for remote accessing devices that are, well, within the same room, right? Uh, within the same rack of equipment, even, where you're not so much worried about physical security being compromised. That's where I was going with that sentence. Port 25, that's SMTP, Simple Mail Transfer Protocol. It's for email. Port 53 is DNS. Note 53, unlike the rest of them are all TCP to this point, right? DNS uses UDP or NTCP. It could be both. DHCP uses port 68 and 67. UDP 69 is TFTP. Port 80 is HTTP, which is plain text over the internet. Hypertext Transfer Protocol. That's what your web page is using, right? Alternatively, you might be using HTTPS, Hypertext Transfer Protocol Secure, and that uses port 443. Both of those are TCP. POP3 and IMAP, those are both for email, Post Office Protocol version 3 and Internet Message Access Protocol respectively. The POP3 uses port 110, IMAP uses 143. These are for remote accessing email. And SNMP, Simple Network Management Protocol, that's UDP, and that uses port 161. Now, how do you know what ports are in use on your device? Well, you could use a handy tool like Netstat. And you can see what's going on. So for example, running Netstat here, we see we've got NetBIOS, we've got a couple HTTP sessions because we have a couple pages open. Oh, there's some more HTTP down here. We got lots of web pages open. So every single application process running on a server is configured to use a particular port number. Individual servers can't have two services assigned to the same port number on, well, the same server, right? Just can't happen. Active server applications are assigned a specific port, and that's considered open. So it's accepting requests on that port. Any incoming client request addressed to that port is accepted, and then the data is passed to the server application, processed, and a response is formulated. So here we see we've got a server. It looks like it's running email, and it's also running email and web, right? It's a web server with email configured. So this client is requesting a web page using port 80. Means it's running HTTP, so no encryption. Everything's plain text. The source port for the response from the server would be on port 80. The destination port would be whatever the client's random port that it sent in the initial request. It would have sent a source port. So we see, here's the client package down here. I don't know why they didn't put this up there. There's the client's random source port. That's in that random range. Destination port, port 80 on the server. Because this was the source port in the request, that's how the server knows what port to reply to, right? Same thing here. This client is browsing email or doing something with email. So it sends a request to the server, destination port 25, and the source port is the one that's going to be the destination port in the response. TCP uses the three-way handshake to establish a connection. First, it sends the synchronous flag to synchronize our timing and whatnot. It receives an acknowledgement to that sync, SYN, and sends its own. And then we have an acknowledgement and sequence number established, and we've got an established connection, and things start happening. When sessions are terminated, they send the fin flag, That has to be acknowledged because everything has to be acknowledged with TCP, right? That device will send its own FIN flag, and then that's acknowledged again. Three-way handshake, yet again, just the other way to close it. So the three-way handshake, generally when we refer to the three-way handshake, we refer to establishing a device or connection. It establishes that the destination device is on the network, verifies that it has an active service and is accepting requests, and informs the destination that the source is going to establish a communication session and start sending some data. After that communication session is closed, the connection's terminated. If the connection wants to be used, well, a new one has to be set up, right? If the device wants to transmit again. Here's the different control bits that can be in that control bits field. So we have urgent, indicates that it's urgent. Acknowledgement, if it's an acknowledgement packet. Push, if it's a push, requires the push functionality. RST, to reset the connection whenever there's an error or timeout. SYN, to synchronize the sequence numbers used in your connection establishment. And FIN indicates, I've got no more data to send. I'm done. Are you done? Because then we're done, right? We're not done yet. Now, TCP also has a couple more things built into it, like reliability and flow control. So it can help maintain the flow of packets so devices don't become overloaded. There could be times when segments don't arrive in their correct order, right? Or don't arrive in their destination at all. And all the data has to be received and the segments put in the original order. How does it do that? Sequence numbers. Sequence numbers. Sequence numbers are assigned to the header of every single packet. And then those are checked at the destination as part of putting the data back in proper order. This is important because it doesn't matter how well your network's designed, there's going to be some data loss. It's going to happen. So just get used to the fact that it's going to happen, and we've got mechanisms to deal with it. So TCP gives you methods of managing these by using sequence numbers, and based on these sequence numbers, right, there's an acknowledgement number. It's the value of the previous sequence number plus 1, right? The last bit I received, I expect this one. And if you don't get that one, you know something's been lost, and you can request it be resent. TCP also provides flow control. So this allows you to send as much data as possible reliably. Does this using the TCP sliding window. So there's initial window size negotiated. Yeah, I'm explaining this badly, I know. I think we're going to get to the sliding window in a minute. I was expecting to get there and it's not there. The maximum maximum segment size, sorry, MSS. That was on the previous slide, wasn't it? Thought it was. Yeah, MSS 1460. I knew we would get to something here. So that's the maximum amount of data that the destination can receive. With IPv4, it's commonly 1460. Where do we get that 1460? The maximum is 1500 bytes. However, there's 40 bytes of overhead, 20 for the IPv4 header and 20 for the TCP header. So you get 1460 bytes of actual data. When congestion occurs on the network, packets could be dropped by the router that's overloaded. So TCP employs congestion handling mechanisms, timers, and algorithms, and the sliding window. So if data is being dropped or packets are being dropped excessively at the rate that we're sending at, we're just going to slow things down. We'll send slightly less data a bit slower until things are okay. And then we'll try to speed up again and see if it happens again. Hopefully that helps. And I did promise some jokes, right? Some jokes and command line Star Wars. I've got a note in front of me. UDP doesn't bother with any of this, right? It doesn't establish a connection. It doesn't provide, or it does provide low overhead because it doesn't have to manage any of this stuff, right? It doesn't track sequence numbers like TCP. It has no way to reorder data if it arrives out of sequence. It just reassembles the data in the order it's received and forwards it up to the application. So it's a really simple protocol. And it's intended for things that require high bandwidth and to work fast, right? Like streaming video and gaming. UDP uses the same registered ports and well-known port numbers that we saw previously. It's just UDP. UDP will receive a datagram destined for one of these ports, and it forwards the application data to that appropriate application based on its port number. UDP client processes select a dynamic port from the range of port numbers in that dynamic range, right? And that's going to be the source port for this conversation. The destination port, that's usually the well-known or registered port number that's assigned to the server process. So we've got DNS and radius in the example here. DNS is port 53, radius is port 1812. And after the client has selected its source and destination ports, those ports are used in the header of all datagrams in the transaction. So, funny jokes to remember TCP and UDP. The best part about UDP jokes, nobody cares if you get them. And you're sharing a toy with a friend. If you're sharing that toy with TCP, you ask your friend if you would like to share the toy. He asks you if you want to share your toy or he wants to share his toy and confirms. And then you agree and share the toy. If you're sharing a toy with UDP, you throw it in his general direction and walk away. That's TCP and UDP. So hopefully all that made sense. We're going to do a little bit of subnetting, but before we do, I promised you something. I give you the only use I've had for Telnet. Command line Star Wars. And I typed that really quick. I guess if you need to see the command, you're going to have to pause and go back. I'll let this go for a minute or two past the credit sprawl. You can skip ahead if you want to just go right to the subnetting, but I think it's a cool thing. I've only ever let this go for about half an hour before it times out. I don't know how much of the movie they've got in there. Not bad for ASCII art, huh? I'm going to kill it there. Alright, let's do some subnetting. And I'm actually going to leave that there. We're going to start it with a nice easy one. 2 subnets. Then we'll change things up from there. What's our first step? We need our subnet mask, right? It's a /24, so that means our subnet mask, is 255.255.255.0, right? We're going to create two subnets, starting off nice and easy. So we're going to borrow 1 bit, which looks like that. We convert that back into decimal, and we get that right there. And our increment is 128, right? It's the bit value of the last bit we borrowed. Now we got the information we need to fill in our table. Our subnetting's done. It took like 2 seconds. Our network ID for subnet 0 is always the initial reservation. That's what you started with, right? Now, we're incrementing by 128. We're incrementing in the 4th octet. So this one's going to be 192.168.0.128. Whoops. And it's always useful to increment one more time, even if it doesn't exist, right? Now that we have our network IDs, let's set up our broadcasts. So this one's going to be one less than each one's going to be one less than the next network ID in sequence, right? So this one's 192.168.0.127. Come on. I don't know what went on with my formatting here. There we go. I think we're okay now. There! I fixed it. And this one, of course, is going to be 192.168.0.255. See, I like doing this on a board better. I really do. So we've got our network IDs, we've got our broadcasts. We can think of these as our boundaries to our subnet, right? So if we increment one here and decrement one here, we get our range of assignable addresses, right? Our first usable to our last usable. So this one's going to be 192.168.0.1 to 192.168.0.126. Oops. This one's going to be 192.168.0.129 to 192.168.0.254. And we're done, right? Let's reset it and do another one. I'm going to pause for a second, or let you pause, I guess, if you want to take a picture. Right. So let's do, well, the same thing, sort of, but let's make it a little more. Let's not go to 12 yet. Let's do 3 subnets. It's going to change our math a bit, isn't it? So our initial mask, right? Our subnet mask is 255.255.0.0. 2 to the what gives us 3. We're going to borrow 2 bits in this case, right? So that's 255.255.255. Like that. And we'll convert that back into decimal. We get 192, right? 128 plus 64. And our increment is 64. So the network ID for subnet 0 is still going to be 192.168.0.0. We're incrementing by 64. We're incrementing in the 4th octet this time. So that's going to be like that. And incrementing by 64 again. And one more time, right? We actually get 4 subnets. There's all 4 there. Now that we've got our network IDs, we can figure out broadcasts. I'm going to go one more, because again, that would give us 256, right? Which means, can't have that, right? Our broadcast for this one's going to be 255. So this one's 192.168.0.63. This one's 192.168.127. 192.168.0.191. And 192.168.0.255. And then same thing across the board, right? Our first usable to our last usable, we just increment 1 and decrement 1. So this is 192.168.0.1 to 192.168.0.62. And yes, I'm talking but not typing. I'm getting kind of tired because the time change is messing with stuff. I'm going to do one more after this, and we're going to call it a week. Yeah. So, I'm going to pause, or let you pause, take a picture. Hopefully that makes sense. We'll do some more in the lab. Let's go on to another one. Same starting place. Now I'm going to make it 13. So it's going to change our math completely, right? So we identify our mask. Well, it's a /24, so that means it's that there. We just did this, right? Nothing changed except for the number of subnets, which means all of our math is going to change. To the 2 to the n, how many bits do we borrow? To get 13, we're going to borrow 4 bits, right? So that means our new mask is going to look like this now. And if we convert that back up, we should get to 40, right? 128 plus 64 plus 32 plus 16. And our increment here is 16. So we start incrementing the network ID for subnet 0. That's going to be 192.168.0.0, right? Our initial reservation, always, always, always. So it's going to be 192.168.0.16. This is, whoops, not star. 192.168.0.32. And that would be 48, right? And we just keep going up from there. I'll fill in our table this time. We get 192.168.0.15. 192.168.0.31. And 192.168.0.47. Which means this is 2.168.0.1 to 192.168.0.14. This one's 17, right? Oops, 0.17 to 192.168.0.30. And this one should be 33 to 46, right? Hopefully I've done my math right. Looks like I have. I only gave you the first 3 subnets. There would, of course, be 16 subnets here, right? Yeah. So we would have an awful lot more. With that, take care, be safe, have a great week. See you in this week's lab. Yeah, bye for now.